So first of all, you've got function where relation, where each element of the domain is paired with only one element of the range. So that makes the difference with what we're working with today, which are functions, versus the conics that we worked with before. Okay, conics are not functions. Think about like a circle and an ellipse. You have 2 points taking up the same vertical space on a circle and ellipse, because you have a point at the top, a point at the bottom. Parent function is the simplest function in the whole family of functions. And that's what we're working from today. There are 9 different functions we're going to be working with in this unit. When we are finished with that, you will be able to rapidly sketch them. So before, primarily Algebra 2, where we actually graphed these functions, we did make complicated tables, but there wasn't a quick way necessarily that I would call rapid to graph these functions. With your understanding of them a little better at this point, we'll actually look at quick ways to get a sketch of all these functions, of the 9 different functions. So, any questions on this piece? Again, just the fact that the definition of a function, because everything we're working with in this unit is a function. Okay, so these are some of the ones we'll be taking a look at. So go on ahead and start writing these down while I get attended and start on the test. All right, and there's the rest of them. Those are the ones that we'll be working from. We'll talk about what the parent's function or equation is, as well as just the overall look of the graph. Here in a moment. So. Reciprocal.
Okay.
Yes.
Yeah, I wasn't the only one that had trouble. I have bad handwriting, so I can read through.
All right. So constant and linear are very much the same. Constant is a linear function, it's just a specific kind. Where B is just a number value. So those would be your horizontal lines going across the graph somewhere. Linear functions have a slope of 1, and it goes through the origin. Most of these graphs, as a parent function, have a point at the origin that is the focus of the graph. So when we look at absolute value, it's a modification of the linear graph, but it's a V shape. Quadratics and cubic have a curve to them. So you have your standard parabola with a quadratic. Cubic, you have something similar, except it curves both directions. Square root is the inverse of your quadratic function. And we'll be using that fact to come up with its graph. Exponential and logarithmic equations, they're the only ones that are a little different, because your base, y equals 2 to the x versus y equals 3 to the x are both parent functions with different bases. So your base will change on your exponential equations. Logarithms will be the same way. Okay? So exponential equations approach the x-axis at 0. Logarithmic equations approach the y-axis at 0. Reciprocal functions approach both the x and the y-axis. So you have your x in your denominator. So we have a curve in quadrant 1 and a curve in quadrant 3. So 7, 8, and 9, those are often confused for each other. Okay? Exponential equations approach a horizontal line. Logarithmic equations approach a vertical line. And if you see two curves, that's your reciprocal function, where you have the variable in the denominator. It's the only one that does that. Okay. So based on that sketches, looking at the next page, see if we can identify which one's which. Name the parent function. So that would be a parabola. So that would be a quadratic. And write the equation for the parent function. So that's what we do there. So that's what you do for the remaining 5 problems. See if you can match it. The shape of the graph to the name and the equation. All right, so what do we have at number 2?
Linear.
Okay. 3.
Absolute value.
Four.
Reciprocal.
Okay. So the biggest giveaway on this is the fact that you have 2 curves. Five.
Cubic.
And
Third.
yes.
Right?
Okay, square root, very easy to identify. It kind of looks like just half of a parabola, and there's a definite point that it starts at and then goes from there, whether it curves up or it curves down. So just knowing these general shapes, knowing what you're coming up against on these, because we have the transformations of all of them. Now, all that looks fairly complicated, but let's just focus on H and K. So H, that's our left and our right movement. K is our up or down. Those are always going to be the case, no matter what the function is. You have left or right, up or down. So whether it is quadratic, absolute value, it's not squared. It doesn't matter. So within the function operation, which would be either it's being squared, cubed, square root, something, you're still going to have that H and K values there in those places. Now, the other pieces are what it does after that. So whether it's vertically changing or horizontally changing. So in other words, if I put a 2 in front here, that's going to be a vertical change. It's going to increase faster. So that is a vertical stretch. Versus if it was 1/2 instead of 2, that's a vertical shrink. Okay. Horizontal. Horizontal are the ones that you see within the function operation. That's why you see the B inside the parentheses. Okay? So, vertical stretch. That means it's moving closer and closer to the y-axis. Vertical shrink, that's a small value, so it's moving more and more away from the y-axis.
It's opposite.
Exactly. The horizontals are opposite. So if I have it at 2, my graph is, say, if I have 2, it's still going to increase faster, right? But I'm talking horizontal, so it's going to still shrink, but it's moving away from the x-axis. So horizontal. Compression. Versus if I had a 1/2 there inside, it's going to move it closer to the x-axis, right? So that's a horizontal shrink. Here's what you need to focus on. Focus on knowing your vertical stretches and shrinks. Okay? Those are the ones, once we start working with Rapid Sketch, those are the only ones we're going to have. Okay? And then just keep in mind your horizontals are exact opposite. Okay? So know what happens vertically, and then your horizontals are opposite that. Okay? The other thing is if I made one of those negative, where it reflects. Okay? So it's either going to reflect over the x-axis or over the y-axis. So if I made this 2 negative out here, that's going to have it from opening up to now opening down. It just went over the x-axis. If I made the 2 negative inside, I'm changing my x values, right? So I'm changing them from here to here, which, depending on the function, you don't see it changing. We'll take a look at that. Here's what I will tell you. Desmos will be your friend on this, with the parent function and knowing what this looks like, to give you an idea. So what we'll do is taking a look at each of these, what's going on with them, identify the transformation. So, first one's a quadratic. There are 3 things happening to it. We have the 3, the 2, and the 5. So this is where I say that this program, there's the parent function. y equals x squared.
That's what you're saying.
Then the new one, all right. Red is the original parent function. Purple is the adjusted. So first of all, how did it move? Left, right, up, down, what happened?
Up 5 to the right 2.
Okay, so there's the H and K values taken care of. The other piece, we have an opening. So when it went to purple, is it opening wider or more narrow?
More narrow.
So that would be that would be a vertical stretch because it's outside the parentheses by a factor of 3. So the 3 means we have a vertical stretch. The 2, we shifted 2 units right. And 5 units up. So every number that's there that's different from the original parent function has something to do with the change. So if we take a look at number 2, we need to do a little rewriting on 2. Because I don't clearly see what the B value and the H value are inside those parentheses. I'm going to use just a different set of grouping symbols to see the difference. So first, I'm going to factor the 2 out of here. And then x plus 2 squared minus 3. 4 things I need to identify. So when we're looking at that, again, still same parent function. Let's see what color it makes it. What was it?
Minus 3.
-3. Okay. Okay. So the negative outside did what? We flipped it over where? X or Y?
X.
Okay. So we've got a reflection of the x-axis. Do we have it? How did it shift?
To left. And down 3.
Okay. So we have a reflection over the x-axis. We have 2 units left, 3 units down. Then, what about that 2 that we factored out?
That would make it stretch down or shrink more.
It's not stretching closer to the x-axis. It's moving away from it.
Oh, okay.
That is the pain with horizontal. Okay.
It
Again,
doesn't have to like.
it would have to be 1/2. Say it was 1/2, then it's stretching closer to the x-axis.
Okay.
Think about stretching. A stretch is stretching it closer to that axis. Okay? All right. So let's take a look at 3. See what you can come up with on this. We have 1, 2, 3 things. So this is the first one that we're actually going to get to see. You would see the difference between a reflection over the x versus a reflection over the y-axis. All right, so the curve is still going the same direction, so there's no reflection at this point. What does a 2 do to this problem? Vertical stretch by a factor of 2. What about the 5 and the 1?
To the right 5 of 1.
Yes. All right, so looking at this, here's the difference. And I'm just going to do it on the parent function. I'll do it here. There's a reflection over the x-axis because your y values change. That's what a reflection over the x-axis does, is it changes your y values. Reflection over the y-axis,
Well, that's all like.
okay? So when the negative is applied directly to x, that changes the x values. When the negative is applied after the function, after the work with x, then it's your y values that are changed. Okay. So this is where, like I said, Desmos is going to be your friend on this to help give you an idea of what these functions look like. So, let's get all these written down. So we have a vertical stretch. We have a shift of 5 units right. And 1 unit up. Okay, see what you can do with the next 2. All right, so the negative first, we're going to reflect it over the x-axis. If on an absolute value function, if you applied the negative directly to x, it'll go from this to this. It looks the exact same because you just switched the sides. Same thing with parabolas, you won't see the change on the graph if there was a negative inside. The 3 and the 2, we have it shifting. 3 units left. and 2 units down. Number 5, this 3 up here, that's A. For that to be B, it would have to be, say, 2x minus 4. Again, if there's a number that x is directly multiplied by, that would be a B value. All right, so we have a vertical stretch. By factor of 3. And then we have our shifting. 2 units right. 1 unit up. How are we doing that? So far, so good? All right, 3 things going on here. We have a vertical shrink. By factor of 3. You've already told me that it's going to be 1 over something by telling me it's a shrink. The negative under the radical with x, that's a reflection over the y-axis. The negative 1. Shift 1 unit down. Anytime you're unsure as you go through these, again, graph the parent function in Desmos, graph transformed function, and then take a look at how it compares. Where did it move from the original location? Some of these are easier to see than others, especially if it has a vertex of some kind, a y-intercept, or like the square root functions, it has that starting point. Those are easier to see. All right, so now you're going to be given the transformation. Plug all those pieces into the equation. So we have this. So really we just need to identify what they gave us. A, B, H, or K. So vertical stretch by a factor of 2, A is 2. Horizontal shift right 5 units, so H is 5. That's it, right? Those are the only 2 pieces I need. So that means y equals 2x minus h squared. And that's it. So identify what you have and then plug in the pieces where they go. So if we take a look at 8, vertical shrink by a factor of 4. That means it's 1/4. But it's a reflection over the x-axis, so that also means it's a negative 1/4. Vertical shift up, K is 3. That's all I have, so parent function plug in what I've got. -1/4. I don't need parentheses because there's no shifting left or right. And then I just add 3 at the end. So you can come up with where 9 and 10 go with their theses. Horizontal compression by factor of 2. That means B is 2. So this means X is going to be directly multiplied by 2. Vertical shift down 2 units. K is a -2. So Y equals the square root of 2X, and then outside it, -2. Okay, reflect over the y-axis. So that means B is -1. Vertical stretch by a factor of 3. That means A is 3. So Y equals 3. Again, reflecting over the y-axis, that means the negative is applied directly to X, not outside of it. Okay. The last part is from a graph. Can you identify what's going on? Number 13 I'm changing. When we get to that, we'll talk about that one. First thing I look at, is there anything that has changed the shape of the graph? Meaning, does it increase faster or did it slow down? No. And the way I know is if I look to the side here, those curves are parallel to each other. The curves haven't changed at all. So from the original point, or the original y-intercept, how did it change? What's the transformation? It went from what? How many units? What happened to it? Okay. All right, so there's our change. What kind of graph do I have? Nope. Exponential. In this case, the base is 2. So anything to the 0 power is 1. However, 2 squared is 4. So when we're looking at these, figuring out what your base is, the exponential can be a little difficult to work with because y equals 3 to the x is a parent function. Y equals 4 to the x is a parent function. Each new base on an exponential function becomes the parent function. So it changes. Now, 2 units right, that means 2 to the x minus 2. So your h is up there with the exponent, and then any k value is added after. So the next one is a logarithm. This is also a base 2. Did the curve change at all? And here's how I know. From one point to the next, they're directly over each other. They haven't shifted anywhere else. They're in that same position. So, what's the transformation? So my new function don't confuse it for this. If there's a horizontal shift, then the number will be included in the parentheses with x. Since the 3 is added after, then it's x plus 0. Okay. So on number 13, I want you to change the graph so that it now goes through the point 2, -2, and draw the curve that way. From the original point, the new graph went where? Did they go up or down any from the original point? No. But it curves different. So we have a reflection over where? Which axis? It curved over which axis and now curves under which one? All right. This would be a square root. So let's put these in. Y equals, we need a negative in front of the radical, and then x plus 2 for a 2-unit shift. All right. 14. We have a cubic. From the original, we have it shifting down 1 unit. That's it. because they very clearly show you one point to the next. Now, so I know I have this. However, I don't have the same curve. Okay? These are a little harder to see to some degree. But this is a 1/8 change. You won't have too many of these. If you do have any with a vertical shrink, if you do, they're going to be a lot more obvious. With the absolute value with the linear functions, those are easier to see. Here, I have a spread of 1 to get to that point. I have a spread of 2. So it's slowing it down. But again, with cubic, it's triple that, right? So that's why it changes from 2 to 8. Triple that distance. That's why it affects it differently. So, all right. So with your Chromebooks,